Students, welcome back to the part C of today's class. We had learned a few basic things about the nucleus, and let's see what we saw. We saw that the radius of a nucleus can be expressed like this: r0 a to the power 1 by 3, where a is the mass number and r0 is a constant. We also learned that nuclear density is constant, that whatever be the nucleus of whichever element, the density is constant, and the size of the nucleus is very small in comparison to that of the whole atom, and lastly, almost the whole mass of the atom is concentrated at nucleus. So obviously from the third and the fourth we come to know that density must be very big, otherwise how such a huge quantity of mass would be concentrated inside the nucleus. Now students, here I would like to point out something like this is that let us look at a nucleus. A nucleus has got both protons and neutrons. You see there are protons and neutrons. Neutrons of course are neutral particles, but protons are charged particles. So when we have two protons, since protons are positively charged particles, this is a proton and this is another proton, there will always be a repulsion between them, which is our well-known Coulomb repulsion. So the greater the Z, as the atomic number increases, the number of protons increases. So we have a large number of protons here, and we have already learned that this is packed in a very small volume. So obviously, what happens here? So there must be some kind of a force which keeps these together. Together means in spite of the Coulomb repulsion, the nucleons, that is the protons and the neutrons, are so closely packed, there must be some other force here, and that force is called the nuclear force. So nuclear force. So nuclear force is nothing but the force between any two nucleon inside the nucleus. So students, here I have been talking about the protons, but then we also have the neutrons, which are neutral. They of course don't have a repulsion between them, but then they are there. So in order that we have a very small compressed volume, there must be attraction even between the protons and the neutron, and between the neutron and the neutron. So actually nuclear force constitutes all these force: the force between a proton and a proton, the force between the neutron and the proton, and the force between a neutron and a neutron, So you see, and all these forces are, number one, they are attractive in nature. They attract each other, whether they are of the same charge, whether they are uncharged, whether one of them is charged and the other uncharged, it's always attractive. That is the main thing. Secondly, it's also actually the second should come here. It should be short range. I have written it here now. This is a short range. Short range means what? We know that a nucleus, the diameter is very small. Radius is 10 to the power minus 15 Fermi meters. So it's very small. So you see the attraction will be present among this only when they are inside the nucleons. So if I draw a graph like this, between the distance from the center of a nucleus. Suppose this is the nucleus, this is the center of the nucleus, and suppose this distance is r, which is the radius of the nucleus. Then if I take this side as distance from center of nucleus, it is seen that we have a very high value of the force, and then this is the distance r along this side, and r is 0 here, and then till r reaches r is equal to capital R, this remains almost constant, and then suddenly after that it becomes 0. So what does it mean? That means it has got the attraction force of attraction is almost the same from the center of the nucleus. That means if I put 2 nucleons here or I put 2 nucleons here, the attraction between them is the same. But then if one of the nucleons somehow come outside, it cannot pull, the other nucleon cannot pull it back. That means it becomes 0 at the boundary. So that is why it's called a short range attractive force. So that is one point. Number 2, it is also called the very short range repulsive. Now what does this mean? Why very short range repulsive? Okay. Now imagine 2 nucleons placed very close to each other. Too close to each other means, let me draw this so that you'll understand properly. Suppose, okay, let me find some space here. Suppose from inside here, I take out one proton and another proton, and let me draw it here like this. This is one of the protons and this is another proton. Now see, now the force between them is attractive. That means they attract each other. But since the proton has to remain its shape and size, so if the force is decreased beyond a certain, if the distance between the center of the protons is decreased beyond a certain limit, it is said the limit is 0.8 Fermi, then the force becomes repulsive. So I hope you get my point, that if 2 protons are here, if they are inside the nucleus, then yes, they have a force of attraction. If they are like this, these 2 have a force of attraction. But then if somehow they get compressed so that this one and this one tries to distort each other so that the distance becomes less than 0.8 Fermi, now the force becomes that of repulsion. So that is very short range repulsion. Then we must also remember that if one of the nucleons is taken out, then there is no attraction. So the attraction remains as long as it is inside this much radius. That is one thing. Then we have other points coming. That is I forgot to tell you the most important point here. That is that before this point should come one point. It is the strong force. It is a very strong force. Because you see, it has neutralized the Coulomb repulsion, because you see in case of uranium and such other heavy substance, we have got large number of protons, about 92 protons. So if we all of them repel each other by their Coulomb repulsion because of the positive charge, then definitely there will be a tendency to separate them, and had there not been the nuclear force, they would have been separated and we could not enclose them in a very small volume. But in spite of this, they all are enclosed in a very small volume, that is the volume of the nucleus. That means it is a very strong force. Actually, it is the strongest force in nature. So strongest force in nature. Number 4 is that it is charge independent. What do you mean by charge independence? Charge independence means force between a proton and a proton and a neutron and a proton is just the same. So this is called charge independent. That means whether it's a neutron or a proton or a proton and a proton, it's always attractive. It is always short range and always very strong. So the force does not differentiate between a proton and a proton, neutron, or proton like this. Then again, there is another property called the saturation. The property of saturation. And what is this property? Let's see. Saturation, let us compare with the electrostatic force. Let me find some space here. Okay. You see, we know that in case of electrostatics, suppose I have got a positive charge here. You see that the charge slowly, first of all, what happens, I bring another charge here, it will be attracted. And if I bring another charge, that also will experience a force of attraction. Another charge, that also will feel its force. You see, this force will be felt by each of these charges. But then saturation is such a thing that inside a nucleus, you see, inside a nucleus, if I have got a large number of protons, this is one, this is another, this is another, this is another, this is another, this is another. So these are a large number of protons that I am showing. Yes, let us look at this one which has been named as P. See, it has been found that this particular proton attracts only its nearest neighbors and then it becomes neutral. After that, this one attracts only its nearest neighbor and the nuclear force gets saturated. That is meant by saturation. So these are basically some of the points that we can understand, but there are certain other points related to the nature of nuclear force like this. Number 6, I will write it here since there is no space and not even much time. It is spin dependent, which we will eventually learn. What is spin dependence? Spin dependent, and then it is also got exchange nature, so it's called exchange force, which we'll learn in our next class. And we have the non-central force. So I'll stop here. It's also called a non-central force, not a central force. So let me stop here.